Chem 30, welcome to the first topic of Unit 5. We're going to cover acid intro, and we're going to talk about acid theory today as well. So acids are important because they include all sorts of functions related to our biological functions, how we live, the way we taste, our blood pH levels, and a lot of bodily functions, but they also play a role in industrial fields and are responsible for the creation of plastics or oils, or a whole bunch of products that affect our day-to-day lives. So acid-base equilibrium is almost everywhere in real life. So the property of acids and bases, really short here. Physical properties are properties that we can observe without having to change the substance chemically. So acids are corrosive when concentrated. They have a sour taste and a sharp odor. Generally think of something like vinegar. Really, when you smell vinegar, you're smelling an acid, not the vinegar itself. If you had other cleaning acids, for example, if you had access to something called propanoic acid has a similar smell to acetic acid, vinegar, because they're essentially making the same hydrogen gas ions, and that's what we're smelling. So bases, on the other hand, again, are corrosive when concentrated. We see this. Acids are typically more dangerous than a base of the same level of strength, but they're still quite dangerous. Bases are still quite dangerous on their own. And then bitter taste, we can think of this as being like black coffee. Okay, so substances that have a bitter taste, we can generally say that they're basic, while substances, if they have a sour taste, think lemon, we think of them as being acidic. Okay, so the chemical properties are properties that are discovered when the acid or the base is chemically transforming into a new substance. So acids react with with bases to produce a salt and water. An example of this is HCl plus NaOH. So HCl is our acid, NaOH is our base. We get NaCl, which is a salt, and that's in fact a table salt, and H2O. We can do this with other acids. H2SO4 reacts with KOH, and we get no, that's not true. K2SO4 and 2H2O. When this is balanced, this is our salt, obviously right here. So salt is when we've got an anion and a cation, an ionic solution or substance for the most part. Now, acids react with metal to produce hydrogen gas. Mg plus HCl, 2HCl produces MgCl2 and H2, right? This is an example of that. And react with carbonates to produce water, carbon dioxide, and a salt. This is actually what forms caves. So as rain travels through the atmosphere, the carbon dioxide in the atmosphere is picked up, creates a really, really weak carbonic acid. Over millions of years, that carbonic acid will eat away at a type of stone called limestone and create hollow areas wherever it drips onto, and eventually we'll hollow that out and fill it with water, creating underwater caves. Okay, that's how the majority of those are made. Same thing with rain falling into the ocean or carbon dioxide dissolving into the ocean, and the ocean going up and down against cliffs. It's physical weathering is happening there too, but also chemical. It'll slowly eat away at cliffs, and that's how you get those little kind of cliffside caves. All right, bases, again, react with acids to form a water and salt. They also react with fats and oils due to a reaction with the oils. So, for example, soap is a base. When you wash your hands with it, you're actually taking oils from your skin, combining with that base, and creating a kind of chemical reaction that makes it feel slippery. On average, they're generally less reactive than acids, but they're still quite dangerous when they're concentrated, at least. Okay, and that's it for topic number 1. So topic number 2 here, oh, that's a lie. We're going to talk about indicators real quick. So these indicators up here at the top are called litmus indicators. These ones are blue and they turn red under acidic conditions. And these are red and they turn blue under basic conditions. So they're just opposite of each other. Okay, these aren't super useful in most processes because they just tell us whether something is acidic or basic, but they don't tell us how strong they are. So for example, we know that lemons are acidic, but sulfuric acid, the stuff found in batteries, is much more acidic. But you put blue litmus paper into it and it'll turn red, but it doesn't give us some indication of how strong it is. So you kind of go think, okay, well, vinegar and sulfuric acid are both acidic, they're both dangerous, or they're both not dangerous. That's not the case. Sulfuric acid is very dangerous, vinegar not so much. Okay, so if you were to stick red litmus paper into acid, it stays red. If you were to put blue litmus paper into acid, it turn red, and vice versa for a base. Blue litmus paper into a base stays blue. Blue litmus paper into an acid turns red. All right, so this down here is called universal indicator. Universal indicator. The reason why it's universal, you'll see here that these little numbers represent the pH. So you stick this into sulfuric acid, it's going to turn that color. You stick this into drain cleaner, it's going to turn that color. You stick it into pure water, it's going to stay yellow. You stick it into vinegar, it'll be somewhere in this range here. So it'll give you an indication of how strong something is. Hopefully from Science 10, you remember the pH scale, 14 at the top, 0 at the bottom, 7 in the middle. Anything in this region here is a weak acid, and then we got weak bases, then we have strong bases and strong acids. So strong acids are obviously much more dangerous. So if this tells you it's got a pH of 1 all the way down here, you go, oh yeah, I got to be careful with that. But if it's telling you it's got a pH of 6 right next to that 7 mark, well, a lot less dangerous, okay? This is our big slide here. This is one of the most important ones, at least. When we have a solution that contains hydroxide or hydrogen ions. So hydroxide is this OH minus and hydrogen ions is this H plus. We're either going to have an acidic, a basic, or a neutral solution. If they're equal, neutral. If we've got more hydroxide than hydrogen ions, basic. If we've got more hydrogen than hydroxide, acidic. Pretty straightforward there. And this is our pH scale. So down here we've got lots of H plus. Over here we've got lots of OH minus, few H plus ions, and then few OH minus. And you can see that there's a huge range. So battery acid being one of the strongest, water being neutral, drain cleaner being on the top end of things, urine and baking soda, seawater, kind of all, and black coffee, kind of all in that same region. That's what we consider to be weak. And as we move to the sides, it becomes stronger, either stronger base or stronger acid. All right, topic 2, acid theory. We're going to look at two main theories of acids, the Bronsted-Lowry and the Arrhenius model. So it's important to recognize that both of these theories rely on this equilibrium reaction. Water will auto-ionize into hydrogen and hydroxide ions. Now, in pure water, the concentration of the hydrogen is equal to the hydroxide, so it's a neutral solution. When we add other substances, such as an acid like hydrochloric acid or a base like ammonia, then it changes the concentration of these. So if we add an acid, the concentration of H plus is elevated. And if we add a base, the concentration of OH minus is elevated. Okay, so in any given water, like anything in a water bottle here, it will have some hydrogen, some hydroxide, always. And as we add acids or bases, it disrupts or changes those values. So the Arrhenius model are substances that contain hydrogen and ionize to make H plus ions, while bases contain hydroxide and ionize to make hydroxide ions. So for example, an acid would be something like hydrochloric acid, HCl aqueous, decomposes or ionizes to form H plus and Cl minus. So based on the Arrhenius model, this is an acid. So something, just because it has hydrogen, doesn't make it an acid. So CH4 is an example of that. CH4 does not form a carbon anion and 4 H plus ions. So it's not an acid. This does not exist. Okay, so an example of a base would be something like sodium hydroxide or calcium hydroxide. And just as not all substances that had H plus are acids, not all substances that have OH minus or OH are bases. Okay, this is methanol. Methanol is not a base despite it having this OH here. It's connected differently and therefore does not ionize at OH minus. Okay, so here are two examples of an acid and a base. So HNO3 is nitric acid. It ionizes to form H plus and NO3 minus. KOH is a base because it produces OH minus and has OH in it. Okay, that's the simplest definition, the Arrhenius definition. But the problem with the Arrhenius definition is that it limits acids and bases to be in the aqueous state, and we know some of them aren't. Some can be in the gaseous state, and also fails to explain many weak organic bases. So two scientists at the same time in the same year, 1923, came up with a more robust definition of acids and bases. And they talked about the transfer of hydrogen as being more important to this process. Now, they said that acids are hydrogen donors, while bases are hydrogen acceptors. So to identify which is an acid and a base, we have to identify which one is losing H plus and which one is gaining it. Now, I do want to pause here real quick and just sort of say that both of these theories will work. Okay, depending on the substance that we're talking about, we may choose the Arrhenius to explain its nature or the Bronsted-Lowry. There's some faults. They both fail to explain a certain type of compound, and we'll see this later on. But just as you learned in grade 10 and probably physical science 20, the Bohr model, in which we say 2, 8, then 8, we could use that model to do lots of different things. We used it to explain ion charges or covalent bonding. But in grade 12, we obviously talked about the quantum mechanical model of the atom, which explained other things well. Okay, so we use different models to explain different things. It doesn't make them right or wrong. It just makes them well suited to explain something, and sometimes not so much. Okay, welcome back. We've got an example here of a Bronsted-Lowry acid-base reaction that we're going to figure out the acid and the base. So by definition, we know that acids are substances that donate hydrogen, while bases are those that accept hydrogens. So we can see this marked hydrogen in red is donated from the HCl to the H2O, right? We can see that there's just the same form of this written 3 different ways. So when it donates it away, right, H plus is now gone. So that now we've just got a chlorine by itself, so Cl minus, and then we've got an H3O plus. So it gains a 1 charge here and this extra hydrogen. So we have this acid and a base, right? So we can see the base transfers the hydrogen, an acid transfers the hydrogen to the base. Okay, we're gonna make this a little bit more complicated by introducing the terms conjugate base and conjugate acid. So conjugates refer to the species on the product side. So an acid becomes a conjugate base. So if we look at A here, A, when it goes back in the reverse direction, picks up an H. So it's been accepted H plus, whereas this one, HB, turns back into B. So the H goes from that back here, okay? So it is donating. So the acid becomes a conjugate base, and the base becomes a conjugate acid, okay? And we got an example here. We can see the acid, HNO2, gets rid of its H and becomes NO2. The base here picks up that hydrogen, so it becomes H3 plus. So it picks up that hydrogen, becomes H3 plus, and then when we move in the reverse direction, when we move backwards, we can see NO2 picks up the hydrogen, so it makes it a conjugate base, so it accepts that hydrogen, whereas the H3O plus donates that hydrogen away and is an acid, right? So we get that conjugate base, conjugate acid, and we can see that here as well. So what we're going to do here is I'm going to label the top equation as conjugate acid, or acid base, conjugate base, and then you'll do it on the bottom and then identify which one is the Bronsted-Lowry base. So what I like to do here is I identify which species are related and either box them or put a line underneath them of different colors, just so it makes it a little bit easier. So we can see here that the NH3 becomes NH4. So it's accepted, it's gained a hydrogen, okay, which makes this a base. That means if this is the base, the other one should be an acid. So we know that acids donate hydrogen away. So we can see H2O becomes OH minus. So it went from 2 hydrogens to this 1. So this makes this an acid. When we go in the reverse direction, right, so in going backwards, you can see NH4 transforms back into NH3, so it loses a hydrogen or donates it away, which makes it a conjugate. acid. And the remaining one has to be conjugate base, but let's just figure this one out, just to be careful. Bases accept, OH minus transforms to H2O. It gains one hydrogen. We can think of H2O as being HOH. So we just, we got our OH minus here plus this H plus, so it's accepted one. So we get the conjugate base there. Okay, in the bottom, if you just want to pause the video or just pay attention to what I'm doing, it's up to you. We've got an acid here because H2S is related to HS minus. It's donated one away, which makes this an acid. CH3NH2 must then be the base. H2S, or HS negative, transforms to H2S, so it accepts one, so we get conjugate base. And then this must be our conjugate acid. And yes, we can see that NH3 donates one away to become NH2. Okay, so it asks which species is the Bronsted-Lowry base, not the conjugate base, but that Bronsted-Lowry base, which makes it CH3NH2. That is our answer there. Okay, identify the conjugate acid base pairs. All we're going to do is label acid base, conjugate base. So HF, we can see that HF is related to F. It's donated one away, right? So the H is gone. It's lost an H, which makes this an acid. This then is a base. F minus accepts one, become HF. So we get conjugate base, and this is our conjugate acid. Nothing too difficult there. All right, so you got this blank slide. The reason this blank slide exists is because there is an inherent weakness in both of these models. They fail to explain one type of substance. And while it's not important necessarily in this particular topic, it is important that we understand it because we're using both the Bronsted-Lowry and the Arrhenius model to predict and write reactions. So the Arrhenius first. So the Arrhenius model states that acids ionize to form H plus, bases ionize to form OH minus, and then the Bronsted-Lowry definition states that acids donate H plus, bases accept H plus. Okay, so what I'm going to do here is I'm going to write out 4 substances. I'm going to choose a strong acid, a weak acid, a strong base, and a weak base. And we're going to see if we can write out these expressions to see how this might work. So our strong acid is going to be HCl. Our weak acid is going to be acetic acid, CH3COOH. Our strong base is going to be sodium hydroxide, and our weak base is going to be NH3. Now, if you're looking at this one and thinking, well, why did I write it like this, CH3COOH? Is because in organic chemistry, we generally write functional groups in a specific way. So if you recognize this, this is a carboxylic acid. And it's really this OH right here, if I want to draw this a little bit differently, it's really this thing here that produces the hydrogen. So this H, and I'll write it in red here, is the one that comes off in order to make an acid. So it's this kind of H right here that we're going to be playing around with in just a second. So we're going to draw all these out. So A, really easy, HCl, according to the Arrhenius, and we're going to draw the Arrhenius over here and the Bronsted-Lowry over here. But the Arrhenius model says that acids are substances that break down into H plus, and we've got exactly that. So the Bronsted-Lowry, the Arrhenius model for HCl works, no problems there. Let's try a weak acid. So weak acids, and we'll see this a little bit more specifically later on, they create equilibrium. So we use that double arrow, but it breaks up into CH3COO minus and H plus. And again, we have a substance that contains hydrogen and it ionizes to form H plus. Just missed the H plus there. There we go. Okay, so we've got a substance that contains H plus and it ionizes to make H plus. So this works out. Next, we've got strong bases. So according to the Arrhenius model, strong bases break down or contain OH minus and ionize to form OH minus. And we've got exactly that. So what works out and then we've got weak acids left. So the last substance that we have here is NH3. So remember, the Arrhenius model states that try it one more time here. The Arrhenius model states that bases contain OH minus and ionize to form hydroxide ions. NH3 we know is a base because if we stick indicator paper into it, it shows it as a base, but it doesn't contain OH minus, so it doesn't work. So we can't use the Arrhenius model to do any weak bases. We always have to use the Bronsted-Lowry. Okay, so it works for weak acids, strong bases, but not weak bases. All right, let's try the Bronsted-Lowry. So we've got first here HCl. So remember, the Bronsted-Lowry involves transferring to something. For this class, we're always going to be able to add water into the equation. Okay, so if we add water to this, we got HCl plus H2O turns into H3O plus and Cl minus. And this works, okay? So the Bronsted-Lowry works for strong acids. Now you're thinking, well, one of those makes H plus and the other one makes H3O plus. Which one is right? How come we can't show that? Well, H3O plus is unstable. So immediately it breaks down into H2O and, oh, I need to drop that, H2O and H plus. So these sort of cross out. If you imagine this being like the net ionic equation. So all these substances cross out. And what do we see here? We see HCl on this side of on the reactant side of the arrow. And then we see H plus and Cl minus on the product side of the arrow. So all those cancel out. So really it's the same thing. It just shows it differently. Okay, so the Bronsted-Lowry can be used for strong acids. Let's take a crack at a weak acid. So CH3COOH, and we add that to water again, and we get CH3COO. So it transfers it away and H3O plus. Again, no problem. H3O breaks down into H2O and H plus, so it's the same thing. So that works. The problem is we've got a base here. Okay, so this is a strong base. If it transfers just a hydrogen away, right, or accepts a hydrogen, then we get NaOH2, which this doesn't exist, and OH minus. Okay, so that part would be okay, but this compound is not a thing. It does not exist. But it has to in order for Bronsted-Lowry for it to work. So we've got sort of a problem here. In reality, the Bronsted-Lowry does not explain strong bases well or at all. So we don't use it. So strong, we'll write NaOH, and then we're going to put a red X here, showing that it does not work for strong bases. Okay, let's take a crack at weak bases though. So NH3 plus H2O produces NH4. This is a real thing, and OH minus. So we can see that, remember, when we've got a basic substance, it produces OH minus ions, or it influences the concentration of the OH minus ion of water. So this works out. We can use the Bronsted-Lowry to explain weak bases. So check mark here. Okay, so we've got three things it works for, one thing it doesn't. So if we're drawing a little Venn diagram here, if we're drawing a little Venn diagram between the Arrhenius and the Bronsted-Lowry, they both work for strong acids. They both work for weak acids. Arrhenius only works for strong bases. The Bronsted-Lowry only works for weak bases. Okay, so when you're doing your practice questions, if you have anything involving a strong base or a weak base, you have to use either the Arrhenius or the Bronsted-Lowry in order to answer that question. Otherwise, you're just going to get a wild sort of answer that doesn't make any sense. Okay, so what we're going to do here is we're going to write the ionization reaction for hydrochloric acid using the Arrhenius, and then we're going to do the same thing using the Bronsted-Lowry. So the Arrhenius is the simpler one. So HCl breaks down into H plus aqueous and Cl minus aqueous. Okay, so let's just double check that that matches the definition. The definition of the Arrhenius is substances contain H plus, check. And it ionizes to form H plus ions. Check. All right, so for the Bronsted-Lowry, we're going to take the same substance, add it to water. Now, water is always written as a liquid. It's a pure substance, breaks down into H3O plus and Cl minus aqueous. So, according to the Bronsted-Lowry definition of strong acids, it donates hydrogen away, which we see it's done here. The HCl has donated its hydrogen to the H2O to form Cl minus and H3O plus. So this works. All right, so amphiprotic substances are substances that can either act as an acid or a base. And a good example of this is water. So when water is combined with HCl, it acts as a base, right? So we can see that it accepts a hydrogen to form H3O plus and Cl minus. And when we add water to NH3, it becomes OH minus and NH4 plus. We can see that it donated a hydrogen away. Okay, so when it acts as a base here and an acid here, it has this amphiprotic quality. It can either act as an acid or a base depending on what it's combined with. HCO3 minus is the same way. When it's combined with H3O plus, it produces this. So in this case here, we can see that it accepted one, that makes it a base. And in this situation, it donated one away to become CO minus. It loses that H, so that's an acid. So again, we can see how it sometimes acts as a base, sometimes acts as an acid. All right, last slide here. We are going to figure out the conjugate base of these four species, the conjugate acid of the four below, and then write out the amphiprotic reactions for the hydrogen sulfate ion. Now, there are a couple of practice questions related to this, but all you really need to do is give yourself a bit of a translation above the question. So it says, what is the conjugate base of these things? So the conjugate base, so acids donate H plus to form conjugate base. So all we're doing here is taking one of those hydrogens off and then dropping the charge, right? So hydrogen is a +1. So we're going to lower the charge. If it's neutral, it goes negative. If it's positive, it goes down 1. If it's negative, it goes down further. So HClO4, we take that hydrogen off. We got ClO4, and now it was neutral, -1 now. H2S, we're going to drop the number of hydrogens by 1. So we got HS minus. We're going to take that one of those hydrogens off. So this becomes neutral and pH4 plus. And then finally, we're going to take the one hydrogen off, becomes CO3 2 minus. So those are the conjugate bases of those four substances. It says, what is the conjugate acid? That must mean these are all bases, and bases accept H plus. So if Cn minus was to accept, it would become HCN, and we increase the charge by 1, so it's -1. Add +1 to that, becomes neutral. SO4 becomes HSO4 minus, so we drop the 2 to a -1. H2O becomes H3O plus, and finally HCO3 becomes H2CO3, and we drop that negative charge. And again, we can see this amphiprotic substance here. In this case, we lost a hydrogen to form CO3 minus. In this case, we gained a hydrogen. So we can see that sometimes this carbonate ion, this hydrogen carbonate ion, can accept or donate based on what it's combined with. All righty, last question here. We're going to write both the equations with water where hydrogen sulfate ion acts as an acid in the first case and a base in the second one. So we should recognize that when it acts as an acid, so we're going to take our HSO3 minus aqueous, and we're going to combine it with water, H2O liquid. If it's acting as an acid, it's going to donate away. So this becomes H3O plus aqueous and SO3 2 minus aqueous. Okay. So it donates it away. It doesn't matter the order that we put this in. H3O plus could come second, or SO3 2 minus could come first. It doesn't make any difference for us. So we're going to start the same way with the second one. HSO3 reacts with H2O liquid In this case, it's acting as a base, so it's going to accept. So it becomes OH minus, so the hydrogen is going to be pulled away from the water and given to the HSO3, so it becomes H2SO3, and then no charge aqueous. All right, so here's the tricky part here. For this first couple of topics, I'm not going to be particular about the type of arrow that you use. We'll learn more about that later on. So if you've seen me use sometimes a single arrow and a double arrow and you're kind of confused as to why, don't worry about that so much. We'll cover it in topic 3. All right, that's it for topic number 2. So if you have any questions, please email me. Otherwise, have a great night. Chem30.